My name is Tomas Persson. I'm a cognitive scientist from Lund University, and I'm focused on primate cognition, or animal cognition in general, but mostly on primate cognition. We have recently started to call our area cognitive zoology. It's commonly called comparative cognition or comparative psychology. But we do more than just comparisons, and we do more than just experimental psychology, which is the dominating method in comparative psychology. And this talk is a little outside of my comfort zone, since I will not talk about my own particular studies, but talk about the problems of explaining other species' cognition. On a meta level. So the question we are grappling is how do great apes explain the world? And to answer that, we of course have to be very wary of our methods for explaining what we see in our animals. So the first part depends on the latter part in this title. And I will not talk much about, or anything about the first part, since I'm very critical about the second part, but hopefully I will give some future directions that might be a bit more positive once I start out with there. So we do research to explain how great apes think. The researcher, as you know, has two goals: find new things and make sure that those things are true. That's basically what a researcher does. And for the latter part, to make sure that things are true, we have a scientific method, which in psychology, and experimental psychology is, or in most science, is hypothesis testing. And sometimes hypotheses, like the hypothesis that orangutans can't swim, can be refuted by one single occasion of an orangutan swimming, so, that we have here in this picture. It was a well-known truth that great apes can't swim. If you throw all the great ape species, if you throw them into the water, they would sink like rocks, including humans that haven't learned to swim. But then, spontaneously, in Borneo, a few orangutans started to swim in a particular context. So then the new questions arises: why can these orangutans swim when the truth about the species orangutans is that orangutans as a species cannot swim? We need theories that can explain all variations of behavior. That doesn't make this an outlier or strange occurrence, but actually explains also why this orangutan swim. And that's a little bit problematic, because in psychology, the most common way of testing hypotheses is to isolate variables and to manipulate those variables. That is a controlled experiment. Where the control is about keeping track of those variables and making sure that it's a replicable or repeatable experiment that other people also can perform. Now this is a fairly idealized picture of experimental endeavors. But in theory, that's how it is. And in psychology, the dependent variables are invisible mental phenomena that we study through their behavioral expressions. And the requirement for good experiments is that the variables are well defined and hopefully are actual stuff that actually exists. So just dreaming up the concepts such as self-control, find the behavioral correlate to this concept, and find ways to manipulate this now invented variable is not always the best way to understand what's really going on. Still, that's what experimental psychology scene first, and then observe what happens. And hope the observations say something about original questions. So we have a mapping problem between inferring mental phenomena that we give a name, like self-control, and then the behavioral correlates for this. And of course, a lot of our research endeavors in psychology is to make sure that these traits, like self-control, that we infer are there, that they stay constant across different contexts, so we can talk about a functional module of some kind. So we change this and that and see if the effect is still there. And then we say that we actually found something, and then we get trigger happy. I want to see if we can find it in other species. Now we found self-control in humans, and I want to see if parrots have it. So we see it like something, an adaptation module, an evolved, discrete thing that we can study in different species. And when we apply it to animals, we of course run into problems of studying non-linguistic subjects, like what you do in infant psychology. So we're limited to performance to how to actually do different tests that we are supposed to measure different things. And here's a recent example that happens to be the same one that was used this morning on intelligence. So this is about the evolution of self-control. And what we do when we compare species, the reason that we compare species, in my view, is the only reason could be an evolutionary question. To see, in this case, we want to see when certain traits has evolved. We compare many different species. This is, I think, the biggest comparative study that has ever been done. It's on 36 species, 567 individuals in total have been tested. However, it's on 2 different tests that are set to measure self-control, the A-B task and a transparent tube problem. So from this, the performance on these 2 problems, they conclude that the species with the big red blobs here are the ones that have the ability, and the small blobs, they don't find much evidence for it, although there are still blobs there, so they find some individuals that happen to solve these tasks. It might be by chance, it might be because they actually can solve it. And then we deduce that if 2 very closely related species have the ability, then it's very likely that the common ancestors of these 2 species have the same ability. And if we have one group that have it and one group that doesn't really have much of it, then it's a much lower score for the common ancestor. It's not as likely that the common ancestor has the ability. Here's the actual paper. This is to show how many big names were involved in it. It's all big names from comparative cognition field. And apparently they sign here that they agree that they are studying the evolution of self-control by looking at these 2 tasks in all these species, and contrasting the species to make conclusions about the common ancestors. That's a common description of what I just said. And the conclusion was noticeably correlated with the different ecologies of these species, because that's where the adaptation view comes in. What is it in these species with big blobs? What do they have in common that the species with small red blobs don't have? And the conclusion is the same as we heard this morning. Quote, our results indicate robust evolutionary relationships between dietary breadth, varying diet, and experiments. And like in all psychology, we are comparing populations. In this test, the population are species. So the species level is the population. And that's hardly never anything we use in human psychology. We talk about different groups. We talked about conservatives and liberals earlier today, for example. We hardly say that all humans work like this. We always have defined subpopulations of humans. It's only in comparison to other species that we talk about the human species. But still, traits tend to jump across species boundaries, which makes it questionable to compare species averages in order to draw evolutionary conclusions. Because, as we know, evolution is not about well-defined variables and discrete traits for selection. Traits are always integrated into a context, and the species context is always only one of many other contexts that the trait depends on. I will show this model from Gilbert Gottlieb, who was a developmental biologist. So regardless of whether we think cognition is something that resides in the brain, or if you have a more interactive view of cognition as residing in interaction with the environment, or wherever we find our explanation for cognition, the development of those abilities are extremely complex interactions between our genetic foundations and the genes' interaction with our neural activity and our behaviors in our environment. And importantly, there's feedback from top to bottom as well. So when we learn new things as we develop, that changes the world we live in, which makes new things possible, which changes things, which makes new things possible, which changes things. So it's always a moving, dynamic system that traits develop in. So if you put this in evolutionary perspective, so evolutionary success is about building bodies that can do what the parents did, and thereby repeat the parents' lives and their reproductive success. So you have reproduction here at the end of the development. This is true for every little trait, every single little thing in the body. But if we conflate them into one big model, we have a reproduction in the end here somewhere. And what is transferred is only, of course, the genes between parents and offspring. But what is selected, or has been selected, is, of course, all the dependencies involved in getting the parent to the reproductive stage. The genes alone cannot do anything. They need the rest of the complex, the developmental manifold, as what they call it. Just a quick example to why this is true and interesting and fun. This is a classic example of non-linear or non-obvious variables involved in traits. In this case, it's a very innate trait, which is that of newly hatched chickens that pick for mealworms. And any normal chicken that is newly hatched will spontaneously pick for mealworms after a few hours. But if you put socks on them, they will never pick for a mealworm. And so what developmental biology has shown is that even innate behaviors are dependent on context, because in this case, the feet has always been present when the trait evolved to pick for mealworms. Every chicken has seen the feet So even a very innate trait is probabilistic. It's dependent on having the right place in place where it unfolds. And this crisscrossing of dependencies and non-linear or non-obvious variables makes development exceedingly complex and exceedingly difficult to study. Who on earth would discover that if you put socks on chicken, they will not pick for mealworms? I'm sure this was a chance of discovery. Here's the data if you want it. Now we have the concept of multifinality and equifinality development. That is that something that ends up, the multifinality means that something that has a very similar start can have very different ends depending on the experiences during the ontogenesis. And the equifinality is that something with very different start can converge on a very similar outcome. So in this example, we have two orangutan males who are roughly the same age. One has developed these secondary sexual traits, large chin pouch and the cheek pads, which the other one lacks. And this is a function of testosterone mainly. And it is dependent on the social dynamics that these orangutans are involved in, because there's only room for one of these males in the orangutan. They don't live in societies, but they share space, and they have different areas in the forest, but sometimes they crisscross into each other's spaces. So there is a hierarchy between the orangutans, although they don't occupy the same group as, for example, gorillas or chimpanzees. And can only be room for one of these big males. So the other strategy is to remain underdeveloped. And they can remain like this for all their lives. But they're still reproductive. They can have children like any adult orangutan. And they do have children like any adult orangutan. They have different sexual behaviors though. These rely more on rape, and these more on females are more willing to be reproduced with them. But the interesting thing is, if this one goes away for some reason, perhaps dies in a fight, one of the other ones will quickly, over just a couple of months, will develop the secondary sexual traits through a super surge of testosterone. And suddenly, they become the new king of the jungle. And one can, and people have even suggested that developmental tweaks themselves are the source of new adaptations. It's not changes in genes and mutation of genes. It's a tweak of the dynamic developmental system that suddenly becomes adaptive. For some reason, maybe it might be very adaptive to have this form, and then things will, over time, be tweaked so that more and more genetic force is given to having this form. So we cannot ignore development. And the question then is, what is the orangutan average? If you are to average a species average here, which is the average orangutan? And the idea of developmental stages having different stages in development can have different reproductive successes themselves. It comes partly from Walter Gerstein, who had this nice quote in an early small article, Developmental Biology. So how would we know if the performance of two different individuals on, for example, a task that measures or is set to measure self-control, either it's within species or between species, if this is the result of the same path through the developmental manifold, considering multiplicity and incrementality. We'll take this just to visualize the evolutionary scenario. So again, the orangutan, can the common ancestors orangutan swim or not? If we make a phylogenetic reconstruction of the abilities to swim, what can we say about the common ancestor of orangutans and humans when suddenly an orangutan can swim? Or to make it even more, we can visualize this as well. But the experimental psychologist who compares population means will say that this is atypical and informative about the evolution of orangutans, while the developmental biologists will say that it's normal and informative because it's an expression of the developmental manifold, and hopefully with enough research one can start to pinpoint how this dynamics plays out. It's a very different science from experimental psychology. And it even is applicable to very strange cases like chimpanzees learning language, human-like language. So instead of describing, for describing the evolution of a cognitive trait, we have to assume, or a trait as an adaptation, we have to assume the modularity, and we need to assume some kind of evolutionary history for this module. But we don't have good access to evolutionary history, so we can never explain the population average very well. So what we can do is to describe this dynamic system, hopefully, in which the population average, as well as the outliers, have some kind of explanation. So, but I'm not trained in developmental biology or in dynamic systems theory, but in experimental psychology, so I have myself problems to do this kind of research, but that's what I wanted to bring to the table here today, this problem of population averages and how evolution seems to work. We can take a discussion, or I have it in the movie as well. As we maybe need 6 minutes for it. You decide.
It's for the movie. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Who's against me?
Good. Okay, this is the background for it. There was a study in 2007 where they wanted to look at insight learning in orangutans. So they had a problem with the peanut at the bottom of the tube. The tube is too narrow to get it up with the tube or the fingers. So what do the animals do? This is the first trial of this animal. She takes water from her natural occurring water source in the enclosure. And she uses that to try to get the pin up. And humans have problems coming up with this solution. If you have them, give them a table with different objects, they will try the sticks and the tools before they see the water standing right in front of them and take the water. They wanted to do a follow-up study on this, so they recruited our animals that we work with. We set up a similar pipe here, and here is the water source. And nobody of our animals came up with a solution to use water to get the peanut up. So then the question is, were they stupid, or should they diminish the population average for chickens or orangutans' ability to use water as tools, or how should we deal with this? And this is a little episode, a 5-minute episode I talked about, where we are painting with the orangutans. We wanted, or the keepers wanted her to paint the hand of the orangutan so he could put his hand on paper, and the zoo could sell the papers as orangutan art and make a lot of money. So after trying to get him to do this, they started to play with the brush instead. And gave him the brush, and he took out the brush to the bars and got new color on the brush, and started to paint things and paint himself, and back and forth, getting color from the keeper, like so. And I have cut this movie to keep it short, but in reality this sequence is maybe 20 minutes long. And he started to paint the bottom of his bucket here, the empty bucket. And he played around with the colors in the bucket. And now she wants him to push his hand out again so she can paint his hand. But instead he sits and pees into this bucket of color. And then he very intently explores the content of the bucket. It's unclear if it's because he's exploring his urine or the color and urine. So I cut that part out. Instead I left this piece in when he's getting more color. He, instead of eating the color, which is his most common response, he puts it into his urine and moves it around. Gets a new color. He wants her to put the color directly into the bucket, and she wants the brush instead. Yeah, did you see that he spits the color first into the bucket, and then he brushes himself with it. Now the last, so he's been using urine and saliva to mix with color so far. Different colors. And now he goes over to his water source. Takes mouthfuls of water that he spits into the bucket. So it shows now that he has a big bucket full of red, nice liquid that he has constructed. Very careful not to spill it, so he wants to keep it. And again, he wants. I don't know what he wants. Taste it. And then the female comes and is very interested. Yeah, I maybe cut out the episode where she tried to take his bucket and he took it back. So he clearly wants his bucket with red liquid. And he took her bottom now. So all the pieces of the puzzle to get the peanuts floating is there. At least it was just that he couldn't assemble those resources when he had the task in front of him to get the peanut rising. So even though he didn't show that he understood the potential of water to get things floating, which I no doubt he understands, he understands the ability of water in the form of saliva and urine and from his drinking pool to interact with substances such as color and explore the effect of this. So I could possibly pack this example of interaction with the physical world into something that we can compare between individuals, or even compare between species. How is that at all possible? To construct populations means from a very complex interaction with this, and explain in terms of species adaptations. So I think that we need to look elsewhere for explanations. Thank you.
I'm afraid the movie has taken the time for questions. So I suggest for maybe 1-2 questions before we move to another talk. So any questions?
The question is simple, but comment. How do we understand the succession of life cycles in the quote that you gave? I mean, it's a dynamic complex, but it's a succession, and I would want to know what kind of succession is that. But as far as what you suggest, it's just the dynamics of an ecosystem, and it sprang to my mind that what could be useful since we do not have access to evolutionary history, is that I mean, what this movie shows to me is that the orangutan does not see him as external to the place he is, as probably any species other than the human. I mean, because you were saying that those traits are not, that they're context-based, so that always happens it always happens in an ecosystem, so but it could, if you have a particular species, then you can, in a particular place, then using other sciences, you can actually explore the history, how that place changed, and that could fuel an understanding of how the traits develop of a particular, not species, but just this section of the species. That's just a suggestion. But you could comment on the success.
Start from the end. I'm not sure there are stable ecologies.
No, I'm not saying they're stable. I'm just saying that if you wanted to explain the development of such a trait, you can fuel just biology with historical understanding of the development, because you don't have access to the history of evolution, and there is no reason for the evolution to be the truth. But if you do believe that, and you want to explain the development of a feature that you perceive in an animal that's alive now, you can explore the rocks, you can explore how there are methods to develop a history of a place, of that context in which that particular feature developed. It's just a suggestion. What is this succession?
I mean, there are many methods. If we agree that cognitive traits are adaptations, there are many methods to use. But if we already have a problem with agreeing on that, then it's problematic. But I'm not sure I understand the question for this. We can take that in maybe tomorrow or during dinner or maybe tomorrow.
Okay. So thank you for your talk.
Well, I just want to answer this as well. This is, of course, it's as we have understood the evolution to work always. It's just that it's not all in the genes. It has to be. I mean, it's only relevant if offspring is living this very similar life to the parents. and they might even use electric pressures to make offspring give birth in real life to parents.